In this sort of questions, the next reasonable question a nice inquisitive mind will ask is that, of course, I gave you the proof where we needed the assumption of commutativity. The next question you should ask is that whether this was essential for the proof, whether we can come up with the other proof, where this assumption is not needed. Maybe I'm not smart enough. Maybe somebody else with some effort can produce another proof where this assumption is unnecessary. If you could come up with something like this, it would be a great achievement, of course. On the other hand, if you want to show that actually this assumption is essential for the proof, how can you do that? You can do it by example. You can provide two example of two matrices, A and B, which will ruin this identity and which will ruin this one as well. If you can come up with such an example, it will be a clear evidence that this assumption is essential for this one to be true. And I do have such example. It's a content of part G in the problem 2. And given our experience with the multiplication already, it is relatively easy to come up with such an example. Here's my example. I chose it rather randomly. It was sort of an ad hoc choice, but it was a little bit inspired by my and now our joint experience with the matrix multiplication. If I say, well, I suggest these two matrices, I will compute the left-hand side here. I will compute the right-hand side here, and we will see that actually they will be different. By implication, that will mean that actually this one is also false for these two matrices. Because if this was true, we would have equal sign here. We just proved that. And of course, when I was looking for this example, I was just choosing a matrices which will fail this, and I was hoping, keeping my fingers crossed, that probably this will fail as well. I tried, and I was lucky, apparently. Here we go. A squared times b squared. A squared take b squared. I'm sorry. Last time we discussed it with you quite extensively. It was a content of question 11, in fact. What happens when you multiply matrix with the basis, with the standard basis of the Rn space? Right? If you imagine yourself multiplying A with itself, right? So you have to write A, and next to it will be another A. Let's just do it. I can't do it right now, but let's just imagine that. Imagine you have this A matrix, and you put next to it, on here, another copy of that A matrix. Then, if you treat the column here as a first basis vector of your standard basis of R2, then you will be looking at what? Just imagining here another copy of A. I'll open this. I'll take you through this. Just to make your imagination easy. Here's my another copy of A. Yeah. If I take a product like this, here's my copy. You can treat this one as these columns as the standard basis vectors in R2. And we know what kind of effect, structural effect they do when you multiply them from the right-hand side on any other matrix. What the effect is? We just keep the columns where we have unities, and we vanish all other columns. So when I multiply this column by this matrix, I will keep the first column, and I will vanish the second column. Well, nothing to vanish, actually. It is vanished already. And when I multiply 0 vector, it will be 0 matrix. And that's why the product of A with A square is just A itself. I don't have to take you like with these boxes across with every element of that entry. Just remembering the structural way or the structural effect of the multiplying a matrix from the right by the standard basis column vector helps me. The same story goes with B. Look at this. If I multiply B with B, here it is. Again, I can treat this second factor in a per column fashion. If I do that, first column 0 will produce 0 column. That's why the B square is 0. The effect of the second column, it will filter out the first column of the left factor. But the first column of the first factor is 0 again. That's why the product of B with B is 0. Very interesting phenomenon, actually. With the realm of numbers, within the realm of numbers, you don't have such a paradoxal behavior when you multiply a number non-zero before non-zero number with itself and you end up with 0. Whereas with matrices, here we go. I multiplied B, non-zero matrix, with the B and ended up with a 0 matrix. That's why the left-hand side here, that's why the left-hand side, actually it is right-hand side, this right-hand side, with this choice of A and this choice of B. I don't need this anymore. With this choice of A and this choice of B is this matrix. Now for the left-hand side, here's my computation for the left-hand side. We'll just take you through that. A take B is simply like so, right? There's just only one non-zero element here, which makes it -1. A plus B is the element like so. Again, multiplying these two matrices, we can benefit from question 11 we discussed with you last week. Because I can split this, I can look into the second factor as columns. And we have two first basis vectors. We know what effect they do when you multiply them on any other matrix from the right-hand side. You filter out the first column. So the product of this vector by the whole matrix will be the first column of that matrix. Here it is. And the product of this column vector by the whole matrix here will be the first column of this matrix. Here it is. You can do lots of shortcuts if you master this thing with the basis vectors. And now here's a clear example that the left-hand side does not equal to the right-hand side. That's why this condition, which allowed this equality, that's a proof. Here it is. It is essential condition. If you drop this condition, this is no longer true. Here is example. Oh, part E says this. It's actually very similar to part C. In part C, we just took one of the numerical, well-known numerical identities, and we just try to see what happens if you try to model something with matrices. Part E models another thing. It models this identity, binomial expansion for this square. It takes binomial expansion, and the actual content of part E, it says this: prove that this is true. You will be able to use the binomial expansion in case of matrices, like with numbers. Given that, in fact, it's even stronger than part C. Given that, if and only if, in fact, you see, is equivalence, matrices commute. I suspect that here you can also make if and only if. I think so. I mean, if this identity is true, you can, from that, by some logical argument, you can conclude that A will be commuting with B. So in fact, I can make here double if. You know, if you remember that, these three letters, they abbreviate if and only if. Even though I didn't prove that, I strongly suspect that will be true. And that's a good exercise. You can try that. In part E, in fact, part E makes it explicit, actually. We have a binomial expansion the way we have it with numbers. If and only if matrices commute. One way, the proof this way, forward proof, it resembles this one a lot. We do expansion a few times via distributive law, and at some stage there will be a place where we need to flip the factors around, and that's the place where we'll use the commutativity. Here we go, look at this. Yeah, so I actually have, in my presentation, I split the proof in two parts. So I use this symbol to denote the part which shows, I said forward, I meant actually backwards. When I said, I mean backwards. The backward implication, it resembles this one a lot. So here's my backward implication, and here's the proof for that. Question E, it means, of course, square matrices. Otherwise, this doesn't make sense. And this one doesn't make sense. You think you cannot add them. So just the question E actually only works for square matrices. So here's my backward argument, which shows that this is true, given that this is the assumption. You do the expansion, like with the part E. Here's my expansion. Square is simply just just multiplied by itself. When I do the expansion, here's the expansion of the first bracket. Here's the expansion of the second bracket. It's one application of the distributive law. There will be another two when I expand this bracket and I expand this bracket. Here's my expansion for that. I will use the square as the abbreviation straight away. A times A is A squared. AB, It's from this expansion, BA from this expansion, and B square is the abbreviation here. So we use the distributive law once again, in fact 2 times again. And now, given that you assume commutativity, you can just combine these 2 factors together and you will end up with binomial expansion as it is with numbers. Let's just see what happens when we go backwards, how we can pull this commutativity conclusion out of this assumption. I think similar argument will work here for this second F. So let's just see the implication this way. Look what I say. If you have any 2 matrices, since this expression is well defined, you necessarily will have that you are looking at the square matrices. This is a part A, in fact, of the question 2. Let's just see what else I say. Now it's easy again, because what I can benefit from my expansion here, because this line, these 2 lines, in fact, these 2 lines, they true in any case. I mean, if you remember when I established these 2 lines, I mean that this left-hand side equal to this right-hand side, establishing this statement didn't require any assumptions. We just relied on distributive law. So in fact, I can use this line again. Here it is. If I use that line, I just slightly rearrange the terms here. So I combine all of the squares here and all of the rest of the terms here. If I use that line again, so it's again the usage of the distributive law 3 times. Given that we now assume that the left-hand side equal to the expression like so, I can equate this right-hand side to this right-hand side. Yeah. Well, if I do that, and if I drop the common terms, if I drop the common terms here and the common terms here, if I do this equating, that's what it will give me. And if I cancel one of the ABs on the left-hand side and the right-hand side, that will be the commutativity.